Recording. Okay, so we started last time talking about membrane installation. I'm going to share the screen with you. Um, Let me first bring it in a presentation mode and then share it. This is considered still as emerging technique for desalination. As you probably you may remember from what I said last time that it has been there since several decades, but it has not been used for desalination. It's been used basically for pharmaceutical applications and some for the concentrations of the juice in the industry of the beverages. So that was the type of work of or scope for the MD. And then eventually, with the development of membranes, and specifically the hydrophobic membranes, it has been found to be a suitable technique for water desalination. So far as of today, there's no commercial plant of medium to large production that is producing membrane distillation using the membrane distillation technology. However, there are units now that are being freely available in the market. Maybe last time I talked about two companies, Scarab in Europe. I think it's somewhere North Europe, maybe Norway or something, who's producing this. I'm not sure about the original country of that company. And there's a spin-off which is actually it's doing very good progress in Singapore. The company is Memsift, and it was basically one spin-off that was based on a technological breakthrough, and then they are producing well, progressing well. They lately have. I was trying to buy a unit from them for our labs, but so far I'm not granting the budget to do that. But they are selling sort of pilot units for membrane distillation systems that can produce maybe starting from 100 liters per day to 100 to 1 cubic meter per day, something like that. It's not very large size, but basically it's a considerable size and it's good for small to medium scale operation. And I would think that like the RO, the systems of the membrane installation are going to be basically sort of modular systems, which means that you can add more and more and more units if you are looking for bigger production. So the establishment of the basic idea and principles of operation for the membrane installation are well laid. And there is substantial work in the literature which is coming about different models and enhancements to the membrane distillation systems, including what we are doing here on our small scale research in the university through small projects. And we are learning and progressing with them. I'm going to share with you some of our models and some of our attempts in this idea or in this regard. And then I'll be sharing with you one paper that was showing sort of a breakthrough. It was published last year, maybe in this September or October, by a team in Spain who are running what is known as the Solara Plataforma. It's an institute in Spain, which is being funded by the European Union, basically. And its applications are mainly or solely for solar energy applications, mainly in desalination, power production definitely, and desalination. So this is the work. They are only interested in this kind of things, and they have different types of layouts. I can say all of them are operated by solar energy. They started in the last maybe 2 or 3 years to show interest in the membrane installation, and they have accomplished a system with very good energy recovery in it so that it has a higher goal. So I have a couple of systems that I would like to discuss with you. One of them is DCMD, which stands for Direct Contact Membrane Installation. So we're going to start with this, and then the second one, or the second case study, is going to be an air gap membrane installation. What we're looking for, actually at that time, we're trying to learn about the direct contact membrane installation, try to uh, establish an experimental facility that is dealing with the direct contact membrane installation, and meanwhile try to learn how to write a model. So it was both a combination of work. Part of it was experimental, part was theoretical, and as a matter of fact, we are continuing with this up to now. So continuously, we have something in hand that we are doing in projects related to the membrane installation. We wanted to build a system to see what are the major parameters that affect the system performance. We wanted to learn about the membrane degradation and the effect on different parameters on the system flux and the quality of the water that we are producing, what's happening with the membrane itself, and finally, how we can estimate the gain output ratio of the system just to see how good is it operating. That was basically some sort of the way that we thought about it at the beginning. We have a hot side where heated seawater is passing in. The feed is coming, which is the seawater, M dot feed. It is heated to a temperature somewhere between 60 to 90 degrees centigrade. Again, low grade heating is needed here. It passes across the membrane. This is the membrane that you see here. So the hot water passes through the membrane because its temperature is high, vapor will start to form. This membrane is hydrophobic, meaning that it passes the vapor through it, but it does not pass the liquid. Semi-permeable membrane that allows only for the vapor to pass. As the vapor passes here, we have a flow of pure water, and the condensate is going to join this, which means that the vapor is going to condense in the pure water and we are going to collect it as a product. The membrane itself needs to be supported, although we don't use high pressure for this technology for the membrane installation. We just use normal operating pressure. So we're using commercial pumps that are available that are just to drive the fluid through from the inlet to the exit, and as it passing parallel to the surface of the membrane, the vapor will form, and the vapor is going to go across the membrane to condense on the other side, which is the permeate side. This is a layout of a sketch. It's some sort of a drawn layout for one side of the system, where basically what we have here on the top is a header to collect water, inlet water. Then water will be going down through 3 wide channels, as you can see it here. And then the water is collected here at another header and it's taken out. So there's inlet hot water here. The hot water will go down parallel in these 3 channels. It will be collected in another header and going out. So this is basically from the feed side, the inlet and exit of the system. Then you can see here we have 3, actually we have 3, so 8 nuts and bolts that are there, so that this unit, we have 2 of it. One of them is for the hot side, and then we have a support layer and the membrane, and then we put another unit like this for the cold side, and then the whole thing is compact. So what you see here in front of you is a section, a photographed section of one side in which we have the flow is coming in that header. It will be distributed in these 3 channels. It will be collected here and going out. Actually, this applies to the hot side and also applies to the cold side of the plate. This is the total experimental layout schematic that shows that we have basically a couple of flow loops. One of them is for the hot side, and one is for the cold side. The one that we have in the right here, this is the hot side. Basically, we have a constant temperature liquid bath, so that you have a heater here and a pump. It pumps hot water at a constant or controlled temperature. We buy this unit, right? I mean, as a whole unit, we buy it ready, and the unit here maintains water at the exit at a certain temperature, which is constant at a certain flow rate. We take the hot water, it passes by a feed flow meter just to measure the flow rate, a control valve so that we can control the flow rate. We have a pressure gauge to measure the pressure. We have a thermocouple to measure the temperature. So we know the condition, the status of the hot water, which is going into the system. As the hot water leaves the system, it has lost some energy here due to the heat transfer, due to the evaporation. And then we measure the temperature and we measure the pressure again, and then it's a closed loop sort of thing. So actually, when you are looking at it from the thermodynamic point of view, the mass flow rate into the specific heat, into the temperature difference between the inlet, which is the highest temperature, and the lower temperature at the exit, this is basically the sort of QN that is going to the membrane module. On the other hand, the left-hand side is having a cooling system. We have a unit like this. This unit, by the way, can maintain hot and cold flow rates. So we have a unit like that, and we are maintaining a cold flow rate depending on the temperature that we want. We want, for example, water at 25 degrees to be here, or 20, or 15, or 10, or 5. So we control it in a way that we know what is the temperature that passes here, and through this valve, we control the flow rate. So water will enter here at a lower temperature. It is going to receive energy from the vapor, which is crossing the boundaries to condense, and then water is going to leave at a higher temperature. We take it back again to the cooler so that it will cool down to the original temperature. Remember that for such a layout, the vapor which is passing here, which is evaporates from the hot salty water, it passes through the pores of the membrane and it condenses here. So the quantity of the coolant increases. We start the experiment with a certain level here, and then we are making an opening in this tank. And as the water level exceeds a certain value, then we're sure that the value that has exceeded, this is basically the product that we are getting, and we collect it here. So this is where we are collecting the desalinated water out of this system. So we have a setup through which we can control temperature and flow rate of the hot fluid, temperature and flow rate of the cold fluid as well. And these are the kind of data acquisition system connected to computers so that we can measure and store the readings of pressures, temperatures at different locations in addition to the flow rate.
Excuse me, Doctor. Doctor, which force, what drives the vapor from one compartment to the other? Is it pressure difference, or who we can define it?
It's the vapor pressure difference, which is caused by a temperature difference. You know, higher temperature is corresponding to higher vapor pressure. Lower temperature is corresponding to lower vapor pressure. The difference in vapor pressure is what drives the vapor to go from the high temperature side and pressure side to the low temperature and pressure side. So the motive here is the difference in vapor pressure, which is created by the temperature difference.
Thank you. Thank you.
You're welcome. That was the layout, and that was our first setup of the experiment. You can see here, this is the liquid, constant temperature liquid bath. This is the tank, and it has some sort of a top of the tank. This is the unit which is doing the heating or the cooling, and this is the tank where the hot water is kept or the cold water is kept. It depends. And then the cycles are going through, and this is the membrane distillation unit that we have here. You can see pressure gauges. in which we are measuring pressures at the inlet and outlet of the feed stream, as well as inlet and outlet of the cold stream. And then here we have a way that we can measure the salinity of the water so that we make sure that what crosses the membrane is vapor, so that the quality of the liquid is pure in the cold side. And definitely, maybe it's not clear here that we have several temperatures so that thermocouples do that we can measure temperatures. This is an electronic microscope image of the membranes, and these are the typical characteristics of the membranes. We are talking about a membrane which is made of Teflon, which is the polytetrafluoroethylene membranes, PTFE. And the important kind of parameters we are looking for are the membrane thickness, which is here 154 micrometer, plus or minus 14. The thickness of the active layer. By the way, the membrane thickness here, this is thickness of the membrane and the support layer. The active layer is only 7 micrometer in thickness. The pore size is 379 plus or minus 8 nanometer. The porosity is 80%, which means that if you are talking about a membrane which is 15 by 15 centimeters, then 80% of this area is hollow. It's represented by the pores. Theta is the contact angle. And remember from last time, the contact angle is greater than 90 for hydrophobic membranes, less than 90 for hydrophilic membranes. And the LEP here stands for the liquid entrance pressure, or liquid entry pressure, and the value is 2.4 bar. This is quite different if we are comparing with the membrane used for the RO. The RO is using pressures up to 60 or 70 bars. Here we are talking about only 2.4 bars. When we did the experiments, taking the readings, the parameters that we changed are basically 4 parameters: temperature of the hot side, the feed side; temperature of the cold side, which is the permeate side; flow rate in the feed side; and flow rate in the permeate side. Then what we did also is that we changed a couple of membranes. So 2 types of membranes. Basically, it has increased a little bit. Actually, we started with 1 type of the membrane, the Teflon membrane, with different pore size, and then we changed it, or we went to use another type of membranes, by the way. What you see here is the flux, and the flux you see here, it is measured as kilogram per meter square per hour, which means that the quantity which is given here has been collected in 1 hour. Per meter square, we are not using membranes of 1 meter square. Actually, the membranes are less than that. So we are normalizing our readings to be represented as per meter square or per unit area. So the flux at the y-axis, and the x-axis has the high temperature side, the feed side. We started by 40 degrees centigrade up to 90 degrees centigrade. And it is clear here, the higher the temperature, the higher the vapor pressure difference, the higher the motivation for the vapor to cross the membrane, and the more productivity that we get. So number 1 here is the significant improvement in the performance in terms of the quantity of sweet water or the distillate water flux due to the increase in temperature. As a matter of fact, the most effective parameter that influences the performance of a membrane distillation unit is the hot side temperature. Look at the effect on the cold side temperature. For each one of these, I can use my pointer here. For each one of these, I mean, this change here, going from these 3 symbols, they are representing different coolant temperature. This one is for a temperature of 25 degrees centigrade in the cold side. This one is for 15 degrees in the cold side, and this one for 5 degrees in the cold side. Definitely, the colder the permeate water, the higher the flux, but the changes are not that significant. It's not like changing from 40 degrees centigrade up to 70, for example. You can see there's a significant improvement in the performance that has gone from the vicinity of 20 to the vicinity of 63 times the temperature difference. 3 times the productivity has been obtained from. Let's look at a different way. That if we double the temperature, if we are going from 40 to 80, what happens to the productivity? It increases by almost 4 times. So the most effective parameter can be seen here as the T hot, the hot side temperature. We refer to it, by the way, in the form of T feed. The feed side temperature, this is the high temperature side in the membrane distillation unit. The effect on the cold side is not significant, and this is very important because if you remember when we're looking at the experimental setup I was showing previously, we used to have a heater to heat the water, to the feed water, and we used to use a cooler. The cooler would basically be something like maybe a vapor compression unit, which is energy consuming agent. If we can operate the unit at higher temperature and at room temperature, this is good enough, which means that all the energy you'll be adding for heating, and you will not need to add energy for the coolant. And that's something that we would not know until we run that experiment this way and run at different high side temperature, at different low side temperature, and see the effect of each one of them. The kind of membranes that we have used here was the PTFE, the Teflon membrane with 0.45 microns. What we see here is the cold side temperature. This is some sort of a cross plot of the previous one. Look at decreasing, or actually increasing the cold side temperature. Yeah, we expect the productivity is going to decrease, but look at the decrease. It's not significant. It's not a sharp decrease like this. It is just something like that. So the effect here of the cold side or the cold permeate temperature is insignificant compared to the high side temperature. This is the feed temperature change. Keeping the cold side temperature 5, going from 40 to 70 to 90, wow, the temperature difference is big. Actually, this is 50 degrees centigrade, and this is 70 degrees centigrade, and this is 90 degrees centigrade. Going from 50 to 90 has resulted in an increase of 2.5 the productivity. So this is significant by running at higher feed temperature, and you don't have to worry much about the cold side temperature. Keep it at room temperature, it will not hurt. Here we see the feed flow rate. Increasing the flow rate, increasing the turbulence, which enhances the heat transfer coefficient. It enhances also the evaporation process, but it is less significant compared to the temperature. So I can put it that way. The most effective parameter is T feed. It is followed by M dot feed. The feed flow rate increases with increasing the flow rate, yes. Here we see the permeate flow rate. Look at the permeate flow rate, it's almost not effective. Look at that. The variations which are occurring here are not significant, going from 2 liters per minute to 3.7 liters per minute or so, or 3.65. It's not a significant kind of change. Accordingly, what we have learned from what we have seen earlier is that if we are going to look at what are the parameters that are affecting the unit, we have studied 4 parameters: 2 temperatures, hot side, cold side; 2 flow rates, hot side, cold side. Then what we may notice is that number 1 parameter in terms of effectiveness is the feed temperature, followed by the feed flow rate, followed by the permeate side temperature, followed by the permeate side flow rate. This is the most effective one, and then the effect drops as we are moving through the other 3 parameters that we're studying. What we wanted to see here in this figure basically was, what if we run the unit for a couple of days continuously? Are we going to gain this to maintain the same flux or not? It was obvious here that not really. We have actually witnessed some sort of a reduction in the flux. Here it was somehow significant. We are talking about something like 42%, which means that if you run the unit continuously with seawater with a salinity of 43,000 ppm, which is the salinity of the Gulf here, then the performance of the unit is going to be affected by operation for longer period of time. Why is that? This is related to the concentration of the salt. You have a membrane, basically, and you have salty water passing here. The vapor is going to pass by the membrane, and it will leave high concentration of salt here. That this kind of concentration of the salt, which is higher than the concentration of the salt in the mean feed stream, this is what we refer to as the concentration polarization. And this is one of the major problems that are facing operation with membranes in general, be it MD, be it RO, FO. Concentration polarization is the ghost that we are afraid of. Why? Because it creates some sort of a boundary layer of high concentration salt at the wall, and it drops in concentration until it reaches the free stream or the bulk flow concentration. What's the solution? Solution is backwashing, or maybe doing some treatment for the membrane so that salt would not be there to block the pores. Maybe coating the membrane with something that that would not result in this kind of higher concentration or salt being accumulated on the surface if possible. So these are basically some of the things that can be done to reduce this effect. I have to tell you that it's not only the concentration polarization that has resulted in this reduction of the flux, but the water that we have used. Actually, we sent students and they collected water in buckets from the Corniche or the University Beach, which means that this water has not been treated at all for anti-foulant or anti-scaling or anti-foaming, which means that blocking due to fouling could have occurred. And that's something which is expected in this kind of operation. This is a comparison for the same thing for the 24-hour, for the 48 hours. The one here with the blue thing is the tap water, which has a low salinity of something like 4,000 ppm. And the one down there is the salty water with high concentration. Tap water is less in salinity, and it is basically filtered water, so we don't monitor this kind of significant decrease in the productivity. This is another way to look at it, by looking at how much is the salt concentration in the product. For the tap water, it remains almost the same quality. For the seawater, the concentration of the permeate increases a little bit with time.
Doctor,
yes.
Can't we say with time the water on the hot side is getting less because of the operation, so the effectiveness will go down because there is less water there?
No, it's not getting less, because we are maintaining a constant flow rate. So the water quantity does not decrease. But what happens is the ability of the vapor to cross the pores decreases, maybe because of accumulation of the salt that may partially block the pores that the vapor would pass through. So the productivity gets less because of that, but the feed remains the same.
Okay.
Here we are talking about the salt rejection. We are talking about the salt rejection is decreasing, but look at the numbers. This is 99.98, and this is 99.95, which means that after the 48 hours, still the pureness of the water is ultra. We're talking about 99.95 pure water after 48 hours. So the issue is not that we are worried that the salt can cross the membrane pores. That does not happen. But what happens is the quantity itself of the vapor, its flow gets reduced because of that partial blockage. In RO systems, for example, every few hours they do backwashing. Backwashing, it means that they reverse the operation so that they push the water on the other side of the membrane so that they can dissolve the salts, or maybe rinse the membranes with sweet water so that it can melt the salt and take it away, the salt. So it's a common problem with membranes generally, and this is how it's been dealt with. What we see here is a scanning electron microscope image of different types of membranes. One of them is the PTFE 22 micrometer membrane, and this is the PTFE 0.45 micrometer membrane. This membrane have a bigger pore size compared to the other one, which means that we expect more productivity to be brought from these membranes compared to the other one. However, the pureness of the water that passes this one is better, definitely, compared to the other one. And what we see here is the membranes, while they are new membranes, and after 48 hours of operation, doing again electroscanning microscopic image of it, you'll find that the shape has changed. Maybe concentrations of the salt have been is what we're seeing here, if you compare it to the previous or with the other figure at the left, which means that there's something changes on the surface of the membranes, and that probably to restore it back, you may do some rinsing or backwashing or so. One more thing here is that when we are looking for the inlet temperature of the feed, we have seen previously that increasing the feed temperature, increasing the flow rate, the productivity. We get more distilled water when we are increasing the temperature because we are getting more vapor. But this is on the expense of what? When we are doing more heating, what are we doing? What are we adding to the unit?
Heat input.
Exactly, heat input, we're adding more energy. Remember the gain output ratio, or the GOR. This is the distillate flow rate into delta H, which is the latent heat evaporization, which is fairly constant, divided by Qn. As we are increasing the temperature, we are increasing m dot, but we are increasing the temperature difference. We are increasing more and more here. So this one increases, this one increases. It depends on the rate. Going for temperature from 40 to 50, maybe 55, 60, it's still increasing. So 60 is some sort of an optimum value. If you heat it more, what is going to happen here? The GOR is going to decrease. Does it mean that the productivity is decreasing? No, productivity is still going higher, but the Q in the denominator is getting higher at a bigger rate. So although you are getting more water, but you are not getting it efficiently, you are spending more energy that you don't need. Maybe you can run it or make a bigger system that can operate at 60 degrees centigrade rather than just increasing more and more and more the temperature. So as a conclusion of this part, that was some of our earlier experimental studies on the HDH system, the parameters that affect the performance of the membrane distillation system: feed temperature, feed flow rate, cold permeate flow rate, and finally cold permeate temperature. Increasing this, and that improves the productivity. Decreasing the cold permeate temperature is going to help, but it is an insignificant kind of effect. The effect of decreasing the permeate temperature is smaller than the effect of increasing feed temperature. So do not worry about cooling the permeate side. Put your effort or put your concentration on heating effectively the feed side. So that's the first lesson that we have learned here. The effective feed flow rate are more notable at high feed temperature, which means that if you are at high temperature, increasing the flow rate will be more effective than increasing the flow rate at a lower temperature. The direct contact membrane distillation is able to provide basically pure water, and it is able to handle feeds with high salt concentration. This is important because you don't find so many technologies of water desalination which is able to handle high concentration of feed of seawater. Normally, there is a limit for each one of them, after which problems of scaling and non-condensable gases and this kind of stuff start to affect the performance of the unit. There is a limit for the MAD, MSF, RO to the water that you can bring in. You cannot bring very salty water in, but you can do it for the HDH as well as for the membrane distillation system. The GOR here was somewhere between 0.2, 0.8 and 1.2. And remember, we do not have an effective energy recovery system. Actually, we don't have an actual energy recovery for this system. And this is why the GOR is not too high. The key for improvement of the performance of thermal desalination systems or generally desalination systems is to think of the energy recovery. Energy recovery is essential for thermal system as well as for RO, which is the membrane-based system. Then, after doing that work with the direct contact membrane distillation, we said, let's do another mode, which is basically an air gap membrane distillation, and then eventually the water gap membrane distillation. I talked about both last time as well. So we started design and fabrication of units. We did the fabrication in building one in our workshop here. The membrane, we only bought the membranes. Otherwise, everything we are building from scratch here. We built an experimental setup. We are using basically all the experimental setups that we are doing. The membrane module is made of acrylic or plexiglass. We buy the plexiglass sheets and then we shape it on the CNC machine in our labs, and then we have the unit there is operating. Just having some rubber gaskets and some support material and so on, and then the system is there. And we wanted then to test, actually I'm just combining some of the work that we have done in several projects. We did a single unit and then we started to think of what if we do multiple stages of the membrane distillation system. The layout that we have here is basically for water and air gap. What's the major difference between this and the previous one? The major difference is basically in the direct contact membrane distillation, you have membrane. On the other side of the membrane, you have cold permeate, which is pure. And the left-hand side was going to have the feed, which is the supply, hot seawater coming in. For the air gap membrane distillation, this is not the case. We add an air gap. So after the membrane, there is a certain thickness here that has nothing but air. And then there is a wall, and this wall should be kept cold by running cold water around this wall. So there's no mix between the cooling stream and the vapor which is crossing the membranes. This is not what we have seen in the direct contact membrane distillation system, where basically the vapor will condense in the permeate water, which is sweet water. For this one, we can use any quality of water for cooling, and this would probably give us an idea that maybe recovery of energy can be done this way. So cold stream will come in, and then it will cool that wall, that surface. The vapor will condense on the surface. The surface will get heated because of the latent heat of condensation of the vapor as it condenses from vapor to liquid. And this heat is going to be carried out by that coolant so that to keep that surface at a lower temperature. And something is going to be added to the unit here, which is this green thing here. The green thing here is the gap. We can have a green sheet here of a thickness of 2 millimeters, 5 millimeters, 8 millimeters, whatever. So you create the gap that you want using this. The speaking is very easy, but when you come to look at the number of holes that we have for the bolts here, previously we had a system of total of 9 bolts and nuts. Here we have 4, 6, 8, 10, 12, 14. So are using 14 in a system which is only 20 centimeters by 22 centimeters and a half. Why is that? Because we wanted to control the leakage. So we used like rubber gaskets, and the rubber gaskets are going to be held tight by the bolts and nuts so that we can make sure that the system is not going to leak. The blue thing here is the support layer, which is an additional support layer to support the membrane so that the membranes does not get broken from the difference in pressure across it. That's another exploded view of the assembly that we had. It has gaskets, it has the acrylic sheets, it has the membrane support layer, and it has the gap, and so it has this kind of different elements. And a spacer, this spacer here is the one which is taking care of creating this kind of gap on that side. This is the air gap membrane installation. Air basically is here, the feed is flowing here, the vapor is going to cross, and then the vapor is going to pass through the membrane. It will, membrane pores, it will touch the surface here, which is cold, so it will start condensing, and we are collecting the condensate as our product. On the other hand, I can close that lower opening here. I can make it closed. So the water which is going to condense is going to gather here. It will keep on gathering until it fills the whole area. And when it does, we call it a water gap membrane installation. So additional distillate is going to be leaving at the top. We collect it here as our product. The coolant is running behind this orange surface, orange wall, so it is not mixing with the sweet water. So the coolant could be seawater, for example, no problem with that. This is the layout, again, of the system that we have. And pressure gauges are there to monitor the pressure on both permeate and feed side, inlet and outlet. This is a photograph of the system. It did not change much compared to the previous setup, but what has changed is this. Now this unit is an air gap membrane installation system compared to the direct contact. I mean, when you look at the system as it closed, you'll never know what's the difference. But since you are the ones who built it, so it's a way that we can do the measurement. This is, I mean, a layout that can measure 4 temperatures, and this is the readout. I mean, this one can be connected to the computer, so we can record values of the temperature right away. And the kind of wires that you see here basically are the thermocouples. Results are showing here that testing here is interesting because we are testing several things. We are testing the water gap versus the air gap performance. We are testing the cold side temperature. We are using 5 degrees centigrade cold side, 15 degrees centigrade cold side, and 24 degrees centigrade cold side. So the cold side, we have 3 temperatures to test, 5, 15, and 24. The hot side, we have 50, 60, 70, 80, 90 degrees centigrade. And we are measuring both water gap and air gap. And the results are shown here. Best performance definitely is for the water gap. Having the water gap operating at as low temperature as possible is better, which means that the cold side is cooled down to 5 degrees centigrade. But as we have seen earlier, look for the water gap at 5 and for the water gap at 24. You see the difference? It's almost insignificant. It's not big, which means that, again, it's not worth investing energy in cooling the coolant. Let the coolant run in atmospheric condition, and the energy that you need to spend it in the hot side. And you see here, there's a significant improvement in the performance as the temperature of the feed side or the hot side increases. Air gap performance, it's less, it's weak, but weak compared with the water gap. But the value itself, when we're talking about a performance in the order of 60 kilograms per meter square hour or 55 kilograms per meter square hour, it's not bad. But the one with the water gap has reached 70, so it becomes more significant in that regard. And note a difference here, which is a major difference. We are going to talk about the model in our next class and the parameters that are controlling the model. The mode of heat transfer which is occurring in the gap. If the gap's too narrow, then we are talking about conduction heat transfer. Conduction in air is a resistor. Compared to conduction in water, water has a high conductivity compared to air. K of water is 0.613, but for air it is 0.024. So that a significant, a substantial resistance to the flow of the vapor is occurring in the case of air gap membrane distillation compared to the water gap. Water gap definitely less resistance, so it is the performance is better. And that's another way to look at this unit here. We are just connecting the lines so that you can feel the significant comparisons between water gap and air gap membrane distillation. The water gap is the dotted line, which is here. Look at, it's the top, it's the highest in all, whereas the air gap value is showing the lowest performance here as we compare it. The water gap with 24 degrees centigrade is this line here, whereas the air gap with 5 degrees centigrade is that one, as you can see it here. So definitely water gap is always greater than the air gap in terms of performance. However, we can say that air gap with 5 degrees centigrade cold side is better than the water gap at 25 degrees. So that's it's the issue of what kind of parameters that you're interested in and what kind of comparison that you want to make sure of, or what you want to see. Here again, we are doing a comparison between different types of membranes. We are comparing the membranes which is Teflon versus the membranes which is made up of PVDF, which is some sort of validinyl. I'm not sure about the chemical composition, but you can find it in an earlier slide. We just know it by the commercial name, the PTFE versus the PVDF, and some sort of a comparison is being shown here for the performance. All of them are having the same pore size, but it's a different type of membranes which is being used. And the Teflon membrane is showing superior performance compared with the vinyl based or type of membranes. Again, water gap and air gap for the two types of membranes. We are looking at the effect of the feed side temperature on the performance, and we are using two types of membranes based on the pore size. The membrane with the higher pore size is the membrane that has higher productivity, higher quantity of vapor is passing through the pores compared to the small pore size where it is narrow, so it is allowing less quantity of the vapor to go through. So the pore size has an effect as well. And another interesting result is when you are talking about air gap and water gap. What's the effect of the gap? How much would be the gap thickness? And we can see here, we are testing gap thicknesses starting from 2 millimeters to 12 millimeters, 1 centimeter, 0.2. And you can see here, the highest performance is associated with smaller gaps. Smaller gaps means a smaller resistance to heat and mass transfer. Accordingly, when you look here, you'll find that the productivity for the case of the 2 millimeter gap is the highest. It is basically water gap membrane distillation with a gap width of 2 millimeters. It is the top figure here. Whereas the bottom figure here is an air gap for 12 millimeters. This is the lowest value that you can see it here. So doing the unit, making the gap as small as possible is the key for a better performance. And a general sort of comparison, which is related to the gap side, which has something interesting here. When you are talking about a water gap membrane distillation, the gap becomes effective when you are increasing it from 2 to 4. Beyond 4, the decrease is not significant in the productivity as the gap increases. Remember, it's filled with water, and water has a high conductivity anyway compared to the air. For the air, because the bigger thickness, the bigger the resistance to heat and mass transfer, so it continuously goes down, but not the same for the water. And that's the difference of the properties of the water versus the air. Then we came up with a setup here in which we are talking about three membrane elements that are connected together as a three-stage system. And in the photograph, you can see this three-stage system side by side here. And we did also the air gap and the water gap, and we tested the parallel and series connection. So if we are going to have these components together, shall we connect them in parallel or connect them in series? What are the differences? Let's look at them. This is the hot side. The hot water leaves it. We have basically a valve, a flow meter, and then water is connected, is distributed in parallel. The water is distributed evenly. Part of it will go here, part will go here, and the rest will go there. So we're talking about the flow rate of the water, which is distributed evenly, divided by 3 by this 3 modules. So if I have something like 6 liters per minute leaving here, 2 liters per minute at 80 degrees centigrade will enter here, 2 liters per minute at 80 degrees will enter here, 2 liters per minute at 80 degrees is going to enter here. Whereas, and then as it enters here, what happens? It will leave, and then it will be collected to return back again to the heater. Look at the chiller side or the cold side. Cold water leaves here, flow rate of it at say 10 degrees centigrade will get here, similar quantity at 10 degrees will get here, similar quantity at 10 degrees is going to get here. When we are talking about the hot side, suppose that water came in here at 80, it will leave at 78 or 77 degrees centigrade, only a matter of 2 to 3 degrees reduction here. So it enters for each one of them at 80, it leaves each one of them as 77 or 78. This is not what's happening here. Here we have that 6 liters per minute, all of them are entering in this module. It will enter at 80 degrees centigrade, it will leave at 77 here. And then the quantity is going to enter here at 77, and then it will leave at 73. It will enter here at 73, it will leave at 70 and then gets back. So you need here to heat it from 70 to 80, but here you needed to heat it only from 77 or 78 to 80. So the energy requirements for the parallel side appears to be a little bit less. Is it true like that? Actually, to some extent, because here basically the flow rate is 6 in every one of them. Here the flow rate is 2 and 2 and 2, but what remains here, what gets back is the 6 at a temperature of 77. Here the 6 are coming at a temperature of 70. You need to heat it from 70 to 80. Here you need to heat it from 77 to 80. So from that, it appears that in a glance that we expect the parallel flow arrangement to be better. Look at the chiller side. Here, the water, say we have water at 15 degrees centigrade. It is entering in each one of them as 15 degrees centigrade. But here it is entering at 15. It will leave at maybe 18. It will enter at 18, leave at 21, enter at 21, leave at 24. And then you need to cool it down from 24 to 15. It appears now that the series arrangement is going to need substantial energy compared to the parallel arrangement, so expect parallel arrangement to be better. And this is what you see here. The one on the top is the parallel, so the top is better when we are talking about the flux ratio between them. That flux ratio between, for example, a single unit versus 3 units. Definitely that that parallel one is showing better here. The percentage increase in the flux for the parallel is greater than the series. And when you are talking about the productivity ratio, again, it's the same thing, some sort of a comparison between a single effect and a 3-effect system. So we're showing that we have a superior performance for the parallel arrangement if we compare it with the series one. And that's something that we have seen. You have temperature drop is less, and as the flow rate comes in, then the rate of evaporation is high. Specific energy consumption is another way to look at it. Instead of looking in terms of the goal, we look on terms of, for each cubic meter of water, how much power did it need? And this actually is some sort of a standard way of evaluating the performance of desalination systems across the spectrum. It means talking about units that are operating by pumps, like the RO. There's no GOR there because there's no heat in. So one way to look at it is how much energy you have consumed. So it's been looked at as how much kilowatt hour per cubic meter, and these are the values. Still 7 is considered to be a high value. People now are talking about reaching for a value of below 2 of specific energy consumption kilowatt hour per cubic meter. I have to tell you that in some places of the RO units, the values of the specific power consumption, although they claim it is somewhere between 2 and 2.4, but in some units, depending on the quality of water, can be somewhere like 8. And some plants in the kingdom are operating with this high specific energy consumption, although it is RO units, and this is because of the quality of water, which needs a lot of power to operate it. Fluxes that are obtained from the water gap membrane installation are higher than the air gap membrane installation. The water gap membrane installation is less sensitive to the changes in the gap width compared to the air gap membrane installation. We have seen that. The parallel stage flow connections produced higher flux compared to the series connection. Specific energy consumption for the water gap membrane installation is lower than for the air gap, which means that it is better in energy utilization. The specific energy consumption decreases as we increase the feed temperature. Rate of evaporation is higher. You produce more water. For parallel multi-stage systems, the productivity increase is about 3-folds, while the increase in the parallel in the specific energy is in the order of 50% or less. These were some of the work that we have done later, and we are still continuing with it now. Currently, we're still working with the issue of multi-stage membrane distillation system, and we are connecting it to solar energy. So what you see here is an evacuated tube solar collectors that are used to operate our systems. We have been using this unit for quite a bit, and each time we develop a new membrane system, we test it with the unit here. The figure that we have here is considering some of the modifications that happened in the cold air loop, and currently we are testing a patent that we have released in 2018, and we are doing a couple of projects. One of them is what we call the proof of concept project, in which we are measuring the performance if we use a sweeping gas to take the vapor from here out and use a bubble column dehumidifier for condensing it. A bubble column dehumidifier is expected to provide very high coefficient of convection heat and mass transfer coefficients. And accordingly, we expect the performance of this unit to be higher. And we are doing currently experiments of the proof of concept for this one, where we have Suhaib as a PhD student who has developed the unit, and he's doing the tests currently and proving or getting the performance parameters for this unit. And that's again a multi-stage system, a parallel arrangement with a bubble column condenser or dehumidifier associated. So the issue of condensation of the vapor, we are collecting all the vapor out and we are passing it through the unit here so that condensation would occur in this high heat and mass transfer unit of bubble column. Yeah, I'm stopping here now, and next time we are going to start looking at the model of the membrane distillation system. We'll be looking at the model equations and what are the governing equations and corresponding approximations we do for it. So that's it for today. Unless you have other questions or concerns that I would welcome to hear. So we said next week we are going to have a quiz on Monday, and the homework is due Wednesday, as far as I remember from last time.
Yes, doctor. Thank you.
Okay, thank you.
Excuse me, doctor.
Yes, yeah, go ahead.
Can you please tell us a little bit about bubble column?
The issue of the bubble column is normally it started with, or the idea was obtained when we're looking for higher heat transfer coefficient and mass transfer coefficient. So in terms of having, for example, the condensation occur in the outside surface of a tube where the tube has cold water inside, the idea was, why don't we bring cold water and put it on a porous plate or a perforated plate, a plate with so many holes in, and we are driving the humid air to come from below, and a blower is going to drive this air. It will rise in the form of bubbles across the water. And that means we have a direct contact between the humid air and the water. So the condensation is going to be more effective.
So bubble column is mainly about to increase heat transfer.
About increasing the heat and mass transfer.
Okay, thank you. Thank you.
Yeah, actually, on the other hand, we also, maybe I mentioned that in the dehumidification system, we are working now with the bubble column humidifier, and we showed that there is a significant improvement in the effectiveness of the unit by going from a packed bed arrangement in which we have packing material to a bubble column arrangement. 3 stages bubble column can take the effectiveness to greater than 90%. For that case, what happens? We pour the salty water from the top on surfaces which having very high number of holes, and then we are driving air from the bottom. So air passes through the holes and passes in the form of bubbles through the salty water. So it takes the vapor here, evaporation occurs or humidification of the occur in a much efficient way. And then we are having humid air at the end, at the exit, which is of high in water content.
Thank you very much. Thank you.
Much.
Just a small question. When we introduce air into it, you know, the air is not a good medium to transfer heat. How it improve when you inject air into the, maybe due to turbulence?
Actually, what happens is that we need the air itself to be heated. So instead of just having a surface where the water is going to stay as in the form of a film, and then the air passes through it to be heated and humidified, we are doing it directly by injecting the air inside the water. So the terms of the interaction between them, we are talking about air that will be surrounded by water from all directions. So the issue of heating of the air and humidification becomes more effective. We are comparing that with a packed column in which you have surface of a cellulose which is wetted by water and their air passes through it. Then you don't guarantee that all the air elements or the air molecules are going to be in touch with the water. This is not happening in the bubble.
Okay.
See, because in the bubble you have very tiny holes, so the surface area increases a lot, and accordingly you have more effective process.
Thank you very much. Thank you.
We're not relying for the air to carry the heat from one place to the other. We are relying on the air to be heated itself.
Yes, I got it. I got it.
Okay.
Thank you.
Thank you.
Doctor, regarding the videos, can you upload the new ones?
Oh yes, actually, even I got a notice from the Zoom coordinator or administrator. He wants me to free the cloud where I'm having the videos. So I'm going to download them, and then I will make them available to you, inshallah.